my name's Darren Holmes, and today in AC Electrical Circuits we're going to look at lab number 7, parallel RC and RL circuits. Under objective, it says this exercise examines the voltage and current relationship in parallel RLC networks. It says of particular importance is the phase of the various components and how Kirchhoff's current law is extended for AC circuits. So we're going to draw both time domain and phasor plots of the currents, and we're going to use a special technique to measure the current. We're going to be using current sensing resistors, so these will be explored further in the lab. Under reference sections, you can see we're still referencing Sham's outlines, Basic Electricity 2nd edition, Chapter 15 on single-phase circuits, Chapter 13 on inductance and inductive reactance, and Chapter 14 on capacitance and capacitive reactance. Your textbook in Chapter 13 covers RL in parallel, and these are the formulas. In Figure 13-15, we can see R and XL in parallel, and they give us the phasor diagram and the current phasor triangle. And Figure 13-16 in your textbook shows you that VT, or the applied voltage, and IR are in phase. It shows you that IL lags VT by 90 degrees, and in this example IT lags VT by 45 degrees. But that depends on the components used. Chapter 14 talks about RC in parallel, and you can see Figure 14-19 shows you XC and R in parallel and gives you the current phasor triangle. And your textbook also gives you the formulas to calculate impedance in a parallel RC circuit, as well as the phase angle. Chapter 15 covers RLC circuits in parallel. And Figure 15-5 shows you what happens if IL is greater than IC. So this is an inductive circuit. And Figure 15-6 shows you when IC is greater than IL for a capacitive circuit and what its resultant will look like. In the theory overview, we have to recall that for resistors, the voltage is always in phase with the current. For capacitor, the voltage always lags the current by 90 degrees, and for inductors, the voltage always leads the current by 90 degrees. It says due to phase response, Kirchhoff's current law must be computed using vector or phasor sums rather than simply relying on the magnitudes. So as with all labs, we have a section for equipment and the components we use. So today we're going to be using the KEYSIGHT EDUX 1002G oscilloscope with built-in function generator. And we're going to use the Mastech digital multimeter. Now it's very important that every time you do a lab, you do actually measure your components so you can see if they're within tolerance. And you can see down the side of the page, we're going to be using a 1K ohm resistor and a 10 ohm resistor, of which I've given you the color codes for, so you can easily find these in your parts kit. So my 1K ohm resistor is 998 ohms. My 10 millihenry inductor is 28 ohms. My 10 nanofarad capacitor is 12.75 nanofarads. My first 10 ohm resistor is 11 ohms. My second 10 ohm resistor is 11.5 ohms. My third 10 ohm resistor is 11 ohms. And my fourth 10 ohm resistor is 10.8 ohms. Now since you only need one resistor, take the resistor that is closest to 10 ohms as possible. So this is the resistor I'm going to be using to take all my measurements. So filling in my equipment, you can see the AC function generator and the oscilloscope are both the KEYSIGHT EDUX 1002G. And you'll notice I'm not going to fill in the serial numbers. They're too hard to find and they're not important for this particular lab. My DMM is the Mastec MSM 9803. So under components, you can see my 1K ohm resistor measured in at 998 ohms. My 10 millihenry inductor, and just keep in mind that it's labeled 103. That's in microhenries. It had a DC coil resistance of 28 ohms. My 10 nanofarad capacitor, which is labeled 103, and that's 103 in picofarads, measured in at 12.75 nanofarads. Now I have 4 resistors in my parts kit. I measured each of them. So the first one was 11 ohms, the second one was 11.5 ohms, the next one was 11 ohms, and my last one was 10.8 ohms. So for most of my measurements, I'm going to use the 10.8 ohm resistor since it is closest to the 10 ohms that I'm looking for. We're using 2 schematics today, so we can see figure 7.1 is R in parallel with C, and figure 7.2 is R in parallel with L. Now keep in mind, when we have a parallel circuit, the voltage across both components will be the same and have the same phase angle. The current will be different through each branch of our circuit. So in order to see the current, we're going to use a small sensing resistor, typically of about 10 ohms. So if we put 10 ohms in series with our capacitor, we'll be looking at the phase angle of the current going through the capacitor, and knowing that the voltage drop is across a 10 ohm resistor, we can do the math and come up with the current magnitude. Likewise, we can put a sensing resistor in series with the main resistor, and it will show us the phase angle of the current flowing through the resistor. And then we can use a sensing resistor to measure the total current flowing through both branches and find out what the resultant phase angle is of the total current. So under procedure, step number 1 refers to the RC circuit. So using figure 7.1 with a 10 volt peak to peak 10 kilohertz source voltage, R1 is going to be 1K ohms and C is going to be 10 nanofarads. We're to determine the theoretical capacitive reactance and circuit impedance and record the results in table 7.1. We're going to be using the current divider rule to compute the resistor and capacitor currents and record those in table 7.2. Just keep in mind, phasors are in RMS, but the oscilloscope gives volts peak to peak, so it's best to leave your results in volts peak to peak. So I've given you 2 pages to fill in your calculations, and I've given you the formulas, the formula for XC, Z, and the phase angle, and the current divider rule for IT, IC, and IR. I just wanted to remind you about the current divider formulas. There are actually 2 forms of the formula. The one we use the most is when we have 2 resistors in parallel. So when there's 2 resistors in parallel, we normally use I1 is equal to R2 over R1 plus R2 times IT. And then I2 is equal to R1 over R1 plus R2 times IT. But these formulas only work if there's only 2 branches in your parallel circuit. If there's multiple branches in your parallel circuit, the formula becomes IN, which is the current that you want, is equal to RT divided by RN. So that's the resistance of the branch circuit times IT. So this is called the general formula, and it works for any number of resistors in parallel. The other formula is called the alternative formula, and it's for 2 branch resistors only in parallel. So for our lab, we're going to be using this formula. So these are my calculations for the RC circuit, where R equals 1 k ohm, C equals 10 nanofarad, V in is 10 volts peak to peak, and I have a frequency of 10 kilohertz. Using the supplied formulas, I've come up with XC is equal to 1.6 k ohms, ZT is 847 ohms, and the angle should be somewhere around 32 degrees. Looking at my current divider calculations, I've used the supplied formulas, and for IT, I'm looking for somewhere around 11.8 milliamps peak to peak. Now remember, I'm going to divide this by 10 when I measure it on the oscilloscope, so on the oscilloscope it should be around 118 millivolts. IC worked out to 6.3 milliamps peak to peak, and IR worked out to about 10 milliamps peak to peak. So in table 7.1, I've filled in my theory for XC, Z magnitude, and Z theta. And in table 7.2, you can see I've filled in my theory magnitude for IC, IR, and IN. IN, we calculated the phase angle to be leading by 32.1 degrees, and you need to remember that IC leads VT by 90 degrees in a parallel circuit, so IC should be 90 degrees, and VT and VR are in phase, so IR compared to the input voltage should be 0 degrees. Under procedure, step number 2, we're going to build the circuit of figure 7.1 using R of 1K and C of 10 nanofarads. Now it says a common method to measure current using the oscilloscope is to place a small current sense resistor in line with the currents of interest. That is, to put it in series with our main components. If the resistor is much smaller than the surrounding resistance, it will have a minimal effect on the current. Because the voltage and current of the resistor are always in phase with each other, the relative phase of the current in question must be the same as that of the sensing resistor's voltage. So it says each of the circuit's currents will be measured separately with respect to the source in order to determine relative phase. To measure the total current, place a 10 ohms resistor between ground and the bottom connection of the parallel components. This is shown as SR1. And then we're going to set up the generator to a 10 volt peak-to-peak sine wave at 10 kilohertz. So this is figure 7.1. Here's your resistor, your capacitor, and we're going to put in a small 10 ohm sensing resistor. So if we measure the voltage drop across this sensing resistor, it will give us the current. Remember, current equals voltage divided by resistance, so if the resistor is only 10 ohms, we can take the voltage drop, divide it by 10, and get the current. It's also going to give us the phase angle. We're also going to do the same thing for the resistor and the capacitor. I just want to show you my circuit setup. I have my function generator and channel 1 coming in on the red binding post that goes to this bus line. Remember, it's a parallel circuit. So this is my 1K ohm resistor in parallel with my 10 nanofarad capacitor, and this is my ground line coming in. Now I've used these little links here because this is where I'm going to place this 10 ohm resistor. So I'm going to put my 10 ohm resistor in here, and that's the total current going through my circuit. So I'm going to take my yellow lead that goes to channel 2 of the oscilloscope, and I'm going to bring it over here to measure the total current. So then I'm going to take the 10 ohm resistor out and put it in series with the 1K ohm resistor, and I'll be able to measure the current going through the 1K ohm resistor. Then I'll take the 10 ohm resistor out and put it over here going through the 10 nanofarad capacitor, so I can see the current going through the 10 nanofarad capacitor. So I'll show you that each step as I measure it. So under procedure, step number 3, we're going to place probe 1 across the generator and probe 2 across the sensing resistor, shown as SR1. We're going to measure the voltage across the sensing resistor, calculate the corresponding total current via Ohm's law, and record this in table 7.2. Along with the magnitude, be sure to record the time deviation between the sense waveform and the input signal, from which the phase may be determined eventually. So this is a real close-up of my circuit. You can see that I have my 1K ohm resistor and my 10 nanofarad capacitor, and they're in parallel. And this is my ground line, right? So the black line coming in is my main ground line. And I had a little jumper here taking ground down to the entire bus line. So now what I've done is I've pulled out that little jumper and replaced it with this 10 ohm resistor. So now the yellow wire, which is going to channel 2 of my oscilloscope, is looking across the 10 ohm resistor. Now it's going to be a very small signal. So let's take a look at that on the oscilloscope. So I just want to remind you, when you're doing a lab, the first thing you should do is a default setup and do a factory default setup and say OK, because you don't know who the last person using your scope was, so we need to set it back to factory defaults. Now you'll notice in the bottom of your screen we have channel 1 and channel 2 probes set at 10 to 1, so we need to correct that. So press the channel 1 menu button, go to probe, and where it says probe 10 to 1, select it and adjust that down till it says 1 to 1. Do the same thing for channel 2, probe 10 to 1, we're going to adjust that down to 1 to 1. Now the next thing we're going to do is turn on our wave generator, and it defaults to sine wave. Today we're going to use a 10 kilohertz signal, so I'm going to adjust that for 10 kilohertz. Our amplitude today is going to be 10 volts peak to peak. And make sure there is no DC offset on. So the next thing I need to do is take a look at channel 1. I can see the waveform goes off the screen, so I'm going to adjust my vertical control. I don't want it so small I can't figure out what it's saying, and I don't want it going off the screen. So in this case, for 10 volts peak to peak, if I put it on 2 volts per division, I can see it goes up 2.5 divisions. So that's 5 volts up, 5 volts down, that's 10 volts peak to peak. Now I know all my settings are correct, and the oscilloscope's displaying the correct readings for me. Channel 2, I'm just going to increase the sensitivity a bit. I don't want it looking bigger than my input waveform, so I'm going to set it to 50 millivolts peak to peak. Next thing is my horizontal, so I'm going to adjust that out until I see a couple of cycles. I like to see at least 2 cycles. Now, I can't quite tell if it's going off the screen or not. So one feature of these oscilloscopes is if I press on the knob that adjusted the horizontal, I can now set it to fine, and I can adjust the time per division to something like 25 microseconds per division, and I can see a complete waveform. It starts in the center line and I get one complete cycle and it doesn't go off the screen. So for today I'm going to set mine to 25 microseconds per division, and you can see on my oscilloscope I'm getting 2 complete cycles. So that's 1 cycle, 2 cycle. So I can see it's a repetitive signal. So now I can set it up to do my measurements. So I'm going to press the measure button. And you can see it comes up and defaults to frequency for channel 1 and peak to peak for channel 1. So the next thing I'm going to do is add the measurement for channel 2. So I'm going to select source, channel 2, under type. I don't want frequency, I want peak to peak. So I'm just going to add that measurement in. So now I can see that I've got my frequency peak to peak for channel 1 and peak to peak for channel 2. So to take my first reading, we can see that the input voltage on channel 1, and I've got 2 cycles coming through, and the voltage for channel 2 is across a 10 ohm sensing resistor. I can see that it is leading, and I can see it's somewhere between 117 and 119 millivolts. So I'm going to record this as 118 millivolts. So now I need to adjust my oscilloscope to do the phase measurement. To do my phase delay, I've increased the amplitude per division for channel 1 to 200 millivolts. And to 2 millivolts per division for channel 2. Now it's looking a little blurry, but I'm going to take my cursors at the center of the fuzz. So if I got a fuzzy trace, I'll take it at the center point. I've changed my horizontal scale to 2 microseconds per division to get as much space between the 2 traces as possible. Now keep in mind I'm going through a positive going transition on channel 2 and a positive going transition on channel 1. So by doing this I get the most accurate points when I'm using the cursors, and you can see my delta T is going to be 9 microseconds. In table 7.2 I've recorded my experimental magnitude, and it was 118 millivolts. Remember to divide it by the 10 ohm resistor and you come up with 11.8 milliamps peak to peak, which is right on what we calculated in theory. My experimental delay was 9 microseconds, so 9 microseconds over 100 microseconds, which is the period at 10 kilohertz, times 360 degrees works out to 32.4 degrees, which is pretty darn close to the 32.1 degrees that we calculated in theory. Now under procedure step 5, you can see they're going to ask us to sketch these waveforms, and they want to have a look at IR and IC and IN. So what we're going to do is we're actually going to sketch these now. We're supposed to use IN as your reference waveform, so I'm going to do that right now. So in order to sketch these waveforms, they're going to ask us to use IN as the reference point. So right now I have the yellow trace going through the 0 crossings, so I'm going to use my horizontal position knob just to move the waveform over until channel 2 is going through the 0 crossings both horizontally and vertically. So now when I draw my waveforms, channel 2, which is the voltage drop across the 10 ohm sensing resistor, is measuring the total current input, or IN. Now I'm going to need channel 1, or VN, as a reference for my other two waveforms that I need to draw. And the other two waveforms, you have to remember, are for the current going through the resistor and the current going through the capacitor. So when it comes time to draw them, I'll show you that in more detail. So you can see I've drawn in my waveform, and it goes through the zero crossing because it's our reference, and it's going to be IN, or the total input current. Now I've also sketched in VN, and the reason I sketched that in is because we always have that on channel 1 of the oscilloscope. So while they want us to compare the other waveforms to IN, we need VN so that we have a reference point when we do our next current measurements. So under procedure, step number 4, we're going to remove the main sensing resistor, shown as SR1, and place one 10 ohm resistor between the capacitor and ground to serve as the capacitor current sense. This is shown as SR3. We're going to place a second 10 ohm resistor between the resistor and ground to sense the resistor current, shown as SR2. We're to leave probe 1 at the generator and move probe 2 across the sense resistor in the resistor branch, shown as SR2. We're to repeat the Ohm's law process to obtain its current, recording the magnitude and phase angle in table 7.2. Finally, we're going to move probe 2 so it's across the capacitor sense resistor, shown as SR3. We're going to measure and record the appropriate values in table 7.2. So I've removed the 10 ohm resistor from IT, and I've replaced it with a little black wire link. So that now connects the entire bus line down here to ground. And I've taken out the little link that I had into the 1K ohm resistor and replaced it with a 10 ohm resistor. And you can now see I have the wire coming from channel 2 of my oscilloscope to the midpoint of the 10 ohm resistor and the 1K ohm resistor. So here we have the waveform for the current flowing through the resistor. Now we're using a 10 ohm sensing resistor, and one of the things I want you to notice is the phase angle for this current is identical to the phase angle for our input voltage. Now you notice I still have it shifted over a little bit from when I was measuring the total current. So when I draw this on my plot, you can see it's going to be in phase with our input voltage. So this little current here is IR, and you can see it's fluctuating somewhere between 98 and 101 millivolts. So I'm going to record this as 100 millivolts being in phase, so that'll be a 0 degree phase angle. As you can see on table 7.2, for IR, my experimental magnitude was 100 millivolts. Divided by 10 gives me 10 milliamps peak to peak, which was the same as my theory. My experimental delay, you notice it was 100% in phase, so there was no delay, so it was 0 microseconds delay, which works out to a 0 degrees phase angle. So once again, I've drawn in my waveform for IR. Remember, IR is in phase with VN, which I put in with a dotted line when I was drawing IN, but I wanted IN to go through the 0 crossing line. So you can see that IR is now lagging IN. It's in phase with VN, but it's actually lagging IN. So coming back to my circuit, I've taken the 10 ohm sensing resistor out from the 1K ohm resistor and replaced it with that little link that takes it back to the ground bus coming in. And I've removed the link that was going to my 10 nanofarad capacitor and put in my 10 ohm resistor, and moved my yellow wire, which goes to channel 2 of the oscilloscope, to the junction of the 10 ohm resistor where it meets the 10 nanofarad capacitor. So we're looking at the waveform for IC. That's the voltage drop across the sensing resistor that's in series with the capacitor. You can see that it is indeed leading, and we can see the peak-to-peak voltage is approximately 78 millivolts. So I'm going to sketch this, and you'll notice that my input waveform is still shifted over slightly, just so that my 0 point, both horizontally and vertically, for the input current is maintained at the same spacing from my input voltage. So this should make it easier for me to sketch. So I'm going to do the sketch right now. Okay, so you can see I've increased the sensitivity for channel 1 to 500 millivolts per division. And for channel 2, I've got it set to 2 millivolts per division. And for my horizontal scale, I'm using 6.2 microseconds just to open it up and get my waveforms trying to go through the zero crossing as vertically as possible. Now you'll notice when I try and increase the sensitivity on a very small signal, it actually increases the amount of noise that I can see on it. So I'm trying to get somewhere in between where the noise is. So this is kind of a best guesstimate for me. So the time difference between V in and IC is approximately 24.4 microseconds. So over on table 7.2, I've recorded my IC experimental magnitude is 7.8 milliamps peak to peak. Remember, it was 78 millivolts. You have to divide it by the 10 ohms. My experimental delay was 24.4 microseconds. Divide it by 100 microseconds times 360 equals 87.8 degrees. So you can see my readings from my capacitor are off a little bit. But then again, my capacitance was off a little bit too. So I've managed to sketch in my last waveform, which is IC. So you can see I have IC, which is leading, IN, which is the reference, and IR, which is lagging. Now in step 5, what they're asking you to do is move probe 1 to the resistor's sensing resistor, leave probe 2 at the capacitor's sensing resistor, use the math waveform to calculate IN, and then sketch this waveform using IN as your reference waveform. So here's what they're asking you to do. They're asking you to put in a 10 ohm sensing resistor to the 1K ohm resistor and hook up channel 1 to the midpoint. Then they want you to hook up a second 10 ohm sensing resistor to the capacitor and hook that up to channel 2. So you can see I have the 3 current waveforms on my screen. What we did was we put channel 1, now remember channel 1 is the yellow trace, and that's across the sensing resistor for the resistor. So that is IR. The green trace is across the sensing resistor for the capacitor, so that's IC. Then we turn on the math function, and the operator is plus, because we're adding IC and IR together to come up with the total current in our circuit. So the pink trace is the total current in our circuit. So you can see from this particular set of waveforms that IC is leading the total current and IR is lagging the total current. Now keep in mind when you're using the math function, the operator is going to be plus. Source 1 is channel 1, source 2 is channel 2. And don't forget to set your scale so it matches the scale for channel 1 and channel 2. You want the scales for each of these channels to be the same so that you can compare them visually. Now you can press the channel 1 menu button, and pressing it again will turn off channel 1. So keep in mind channel 1 is IR. Then we can do the same thing for channel 2, and channel 2 is IC. So now we're just left with the total current in our circuit, and we're going to draw it as the reference with it going through the zero crossing line. Then we can bring in channel 1, which is IR, and draw it, and then we can bring in channel 2, which is IC, and then draw it. Now it's kind of hard to draw from all these three waveforms shown on the screen at the same time, so that's why I did it individually as I went through the steps. So you can see here that my first waveform is IC. My second waveform that goes through the zero crossing is IN, and my last waveform that's lagging is IR. I just found it a little simpler to do it my way rather than trying to sketch the whole thing at the end. So under procedure step 6, we're to compute the deviations between the theoretical and experimental values of table 7.2. And based on the experimental values, determine the experimental Z and XC value via Ohm's law. So XC equals VC over IC, and Z equals VN over IN, and record these back in table 7.1 along with their deviations. So in table 7.1, XC equals VC over IC, which is 10 volts peak to peak, because that was our input voltage, divided by 7.8 milliamps peak to peak equals 1.282 K. My Z equals Vn over In, which is 10 volts peak to peak divided by 11.8 milliamps peak to peak, which worked out to 847.458 ohms. And theta is equal to arctan of IC over IR, so that's the 7.8 milliamps divided by the 10 milliamps, and that worked out to 37.954 degrees. So in step 7, we're going to create a phasor plot showing IN, IC, and IR. And don't forget, our phasors need to be in RMS, so we have to take our peak-to-peak voltages, in our case they're peak-to-peak currents, and divide it by 2√2. So I've converted IC's 7.8 milliamp peak-to-peak to 2.758 milliamps RMS. IR becomes 3.536 milliamps RMS, and IN equals 4.172 milliamps RMS. Now I've provided you with some grid paper so that you can plot your phasors. I chose a point midway, which kind of left IR almost dangling off the edge. So IR was 3.5 milliamps, so I went half 1, half 2, half 3, 3.5, got me to the end. And then for IC, it was half 1, half 2, 2.5, about 2 3/4. So that was IC. Then I put a dotted line in for my rectangle, and I drew my line in for IN, and you can see it's not quite 45 degrees, so it is about 32.4 degrees. Under procedure, step number 8, we're now dealing with the RL circuit. So we're to replace the capacitor with the 10 millihenry inductor. This is shown in figure 7.2. And then we're to repeat steps 1 through 7 in a like manner using tables 7.3, 7.4, and our plot will be on 7.2. So you can see I've finished my calculations for the RL circuit with a 1 k ohm resistor and a 10 millihenry inductor. We're still at 10 volts peak to peak and still have a frequency of 10 kilohertz. So my XL works out to 628 ohms. My total impedance of the circuit worked out to 532 ohms. And my phase angle should be somewhere around minus 57.858 degrees. So that means it's going to be lagging. Using the current divider rule, I have calculated IT, IL, and IR. So IT is going to be 18.796 milliamps peak to peak. I'm not going to convert it to 2√2 yet. And I should have a phase angle on it of minus 57.858 degrees. So IL worked out to 15.915 milliamps peak to peak, and IR is going to be 10 milliamps peak to peak. So I've filled in table 7.3 with my XL theory, my Z magnitude theory, and my phase angle theory. So in table 7.4, I've filled in my theory for IL, IR, and IN. The phase angle for IN is going to be minus 57.858 degrees. Remember, IL lags VT by 90 degrees, so for the phase angle for IL should be minus 90 degrees. And VT and IR are in phase, so IR's phase angle should be 0 degrees. So I've now replaced my 10 nanofarad capacitor with the 10 millihenry inductor, and I have my ground going through the 10 ohm sensing resistor to the ground bus, and I have channel 2 of my oscilloscope looking at the voltage across this 10 ohm sensing resistor. So once again, you can see that the yellow line is my input voltage, the green line is the voltage drop across the sensing resistor, and it's sensing the total current in the circuit. So I've shifted it over so that it crosses the zero crossing because I want it to be my reference line when I draw my waveforms. So you can see here I have V in and total current. So total current is actually lagging my input voltage. Now down here you can see the voltage peak to peak for channel 2, which is my total current, somewhere between 185 and 187 millivolts. So I'm going to record this as 186 millivolts, and it's lagging. So to get my phase angle, you can see I've adjusted the vertical sensitivity to 200 millivolts for channel 1 and 2 millivolts for channel 2, just so I get my lines crossing more vertically through those zero crossing points. And you can see between V in and the total current of my circuit, I'm getting 15.2 microseconds. So filling in table 7.4 for IN, I've got 18.6 milliamps peak to peak. I had an experimental delay of minus 15.2 microseconds divided by 100 microseconds times 360 degrees gave me a phase angle of minus 54.72 degrees. That compares favorably to the minus 57.858, which I'd calculated in theory. So remember, when you're plotting this waveform, you want the total current to be the reference point, so make sure you adjust your horizontal positioning so that the total current goes through the 0 point both horizontally and vertically, and that is your reference waveform. So on plot 7.2, you can see that my input current goes through the zero crossing line, and my applied voltage actually leads the total current. I've now replaced my sensing resistor with a little short jumper, so that now brings in ground to the entire ground bus. And I've put my sensing resistor in series with my 1K ohm resistor and moved channel 2 to see the point between the 10 ohm resistor and the 1K resistor. So it's looking at the voltage across the 10 ohm resistor, which represents the current going through the 1K ohm resistor. So now I have channel 2 going across the 10 ohm sensing resistor that is in series with our resistor in our circuit, which is the 1K ohm resistor. And you can see it's kind of bouncing around here between 98 and 101. So I'm going to record this as approximately 100 millivolts. And you can see that IR is in phase with V in. So I'm going to record this as having a 0 degree phase angle. So on table 7.4, I've recorded my IR as 10 milliamps and my delay as 0 degrees. So on my graph paper, going through my zero crossing is I in, and my next waveform is IR. So you can see IR leads I in. I've now removed my sensing resistor and replaced it with a short or a little jumper wire, so it goes from ground to my 1K resistor. And I've now put my sensing resistor in series with my 10 millihenry inductor, and the lead that goes to channel 2 of the oscilloscope goes across the sensing resistor, so it's actually measuring IL. So now I'm measuring across the 10 ohm sensing resistor that goes to the inductor. So the green trace is now representing IL. So you notice it's bouncing around between 159 and 161 millivolts. So I'm going to record this as 160 millivolts. Now you notice I still have V in just off from where the zero crossings were. So I can now sketch this on my plot, and this will be IL in relation to V in. So once again, changing the sensitivity for channel 1 and channel 2 and the horizontal scale. Putting on my cursors, you can see the time difference between channel 1, which is my input voltage, and channel 2, which is my inductor current, is 24.2 microseconds. And because the inductor current is after my input voltage, it is actually lagging, so this will actually be a negative angle. So on table 7.4, I've recorded my IL experimental magnitude as 16 milliamps peak to peak, and my experimental delay as 24.2 microseconds. And remember, it is lagging, so it is minus. And 24.2 microseconds divided by 100 microseconds times 360 degrees works out to 87.12 degrees. And don't forget, it's minus because it's lagging. So repeating step number 5 for the RL circuit, I've moved channel 1 to the sensing resistor in series with the 1K resistor. And channel 2 is looking at the sensing resistor in series with the inductor. So channel 1 is the yellow waveform, so that represents IR. The green waveform is the sensing resistor in series with the inductor, so that represents IL. And you'll notice IL is lagging by 90 degrees. Then we want to use the math function. We're going to use plus. Make sure the scale is the same as the scale for channel 1 and channel 2. We want to use it as the reference point because IR plus IL is the total current, and total current is going to be our reference point. So it has to go through the zero crossing both horizontally and vertically. So IR is leading our total current, and IL is lagging our total current. So finishing off my plot of 7.2, I've sketched in IL, and you can see that my IL is indeed lagging by quite a bit. This is my zero crossing line, so this is IN. IR was leading, so that means that IL has to be lagging. So one of the last things to do is to use your experimental currents to calculate XL, which is equal to VL over IL, which is 10 volts peak to peak divided by 16 milliamps peak to peak, and that worked out to 625 ohms, which is close to my theory. My total impedance is Vin divided by In, which is 10 volts peak to peak divided by 18.6 milliamps, and that works out to 537.6 ohms, which is close to my theory. And theta is arctan, or tan minus 1, of minus IL over IR, which is the minus 16 milliamps divided by the 10 milliamps, and take the arctan of that, and it works out to minus 57.995 degrees, which again is comparable to my theory. So remember to convert your current in peak to peak to RMS. So my IL converts to 5.6 milliamps, IR converts to 3.5 milliamps, and IN is 6.57 milliamps. Now when drawing your phasor, remember your 0 point does not have to be in the center of the diagram. We can put it up here so that I've got 5, 1, 5, 2, 5, 3, 3.5 for my IR, and you can see I have half 1, half 2, half 3, half 4, half 5, half, and we wanted 5.6, so it's approximately there for IL. Then you can draw in your rectangle and complete the line for IN, and you can see IN is a little more than 45 degrees, and we have 54.7 degrees from our calculations. On the last page, we have 4 questions to be answered based on our calculations and observations of the lab. When you've completed the lab, show it to your instructor so they can initial it to indicate that it is complete.